The first reaction that I'm going to cover is the Bischler-Napieralski reaction. So some key things about the reaction is that it involves electrophiles that are amines, so that means, or amide, so that means the oxidation state is 3, and then it's considered a electrophilic aromatic substitution cyclization of beta ethylamines. That's a mouthful. Anyways, so since this is an oxidation reaction, the reagents are oxidative reagents. These are the most common ones that you will most likely see related to this reaction, which are POCl3, P2O5, PPA, TFAA, and TF2O. Here is a zoomed out version of the reaction mechanism that we are going to go over for the Bischler-Napieralski reaction. So if we come in here, this is just obviously the beginning without any of the mechanisms. So this is what is considered like it's a cyclization of these type of compounds where our R can be anything, and also at the alpha position right here from the nitrogen, if there's an hydroxyl group here, another oxidation can occur. In this example, I do not have that. And then here's one of our reagents, POCl3. I drew that out because that will be helpful during our mechanism. And then this is our product. So our first step of our mechanism is quite arrow hefty, but as you can see, we're having our nitrogen push electrons onto our double bond to push the double bond up to our oxygen, which then attacks our reagent and then pushes up on the reagent on our oxygen. So that is why I have that drawn out, because this reagent is very much involved. It is somewhat a little bit like carbonyl chemistry with the pushing of arrows. That's our first step, which yields this. So now we have a positive charge on the nitrogen, and then we have our oxygen that is now attached to our reagent. So since we have a positive and a negative charge happening within this mechanism, that's usually not allowed, we have to push down and we end up kicking off a Cl. So we have a minus Cl just floating around in the solution now. So now this is what this looks like. I drew it like this. The stereochem is not perfect, but I think it's easier to see this way. So this black dot represents a carbon that now has this whole group on it minus this Cl. So now we can just put it as OPOCl2, and then we have our R group. So now this is we're having our double bond attack the carbon and put electrons onto our nitrogen. So we're getting rid of that double bond that's been created, so that we end up closing the ring. That then leads to obviously a plus charge on this carbon. So a base is going to come in and reform the double bond right here with that hydrogen. And then right here, now we need to reform our double bond that is in our product. So we're going to have a base come in and take the hydrogen, put it into the double bond, and that's going to kick off the remaining of the POCl2 that we don't want that was in our reagent, and that yields our product. The second reaction that I'm going to cover today is the Pictet-Spengler reaction. So this reaction is similar to the Bischler-Napieralski reaction as that, except it involves a substituted beta ethylamine, and then all the R groups thus need to be electron donating into the system. And then except the Bischler one used amides, this one is using aldehydes and ketones electrophiles, so that oxidation state is 2. So there's not technically like specific reagents like the last name reaction. However, the Pictet-Spengler reaction needs a carbonyl compound and an acid, and that acid can either be a Bronsted acid or a Lewis acid. Here is a overview of the reaction mechanism for the Pictet-Spengler reaction. So if we zoom in up here, see, this is where everything is substituted. So I just have R1, R2, R3 to show possible groups that can be there. And then here is our carbonyl compound that we need. This is just going to get ran in HCl, and then this is our product. So to start off, our mechanism is we are going to protonate our carbonyl so that our nitrogen can use its electrons to attack the carbonyl center and push off, push up the double bond onto the electrons onto the O. From here, so now this is attached, as we can see. Now our nitrogen is positively charged, so base is just going to come off and take off the hydrogen. A simple deprotonation step. Right here, we are going to reprotonate our O that's now attached in our whole complex, so that we can again use the electrons on the nitrogen to kick it off, because we don't want it. So our nitrogen pushes and then kicks off our H2O. So now we have water floating in our system. Our next step here is I circled, or dotted I should say, the carbonyl center. So we are going to use the double bond electrons from here to attack into our carbonyl center and then push electrons back up onto our nitrogen so that we can get rid of this plus charge on the nitrogen. That ends up attaching our ring right here. And then from here, it's just a simple deprotonation to recreate our double bond to get rid of this carbocation. And then that just leaves us with our product. So yeah, all of our groups didn't really have anything to do with it. Yeah, so that was the overall mechanism for the Pictet-Spengler reaction, and you can definitely see similarities between the Bischler-Napieralski and the Pictet-Spengler reaction with our starting materials. Now that I have gone over both the Bischler-Napieralski and the Pictet-Spengler reaction, are you guys able to name this reaction? You can pause the video to look at it, but the answer is it is a Pictet-Spengler reaction. A quick way to tell is that there is an R group coming off of the alpha carbon, and then also there is a carbonyl reagent in it. Yeah, anyways, I hope this was helpful.